So in this section, we are going to be looking at advanced anti-differentiation techniques. In the previous lessons, we have been finding the antiderivative using our basic antiderivative rules. Now we will explore the anti-differentiation techniques where the basic rules are not easily recognizable. So the main one is the U substitution. So if you can recall that if I take the derivative of a composition like so, it's the derivative of the outside times the derivative of the inside. So we take that concept right there in conjunction with this, the fundamental theorem of calculus here. So if f is an antiderivative of f, then the integration of f of x is capital F of x plus c. So what I can do is I can do a U substitution thing. So if I have a function that has a composition function, and I have the derivative of the inside in this integration, so if I have this format, then I can do what's called a U substitution. You let U equal the stuff on the inside, you take its derivative with respect to x, and you get this quantity right here, and then we just simply do a direct substitution. We will replace the g of x with a u. We will replace the g prime of x dx with du. And so now I have a format that I can actually integrate. I didn't have a rule for this, but now I have a rule for that. And then I can integrate that using the antiderivative of f, plug in u, plus some constant. And then I'm going to replace what was u back into the problem, giving me my final answer. This is U substitution. Okay, so let's go ahead and take a look at some examples. I have quite a few of them here, and we'll just start running through those things, and then we'll go from there. So the first one right here is this. That's what we're referring to. So as we look at this right here, we're going to look for different things where as soon as we see parentheses, just like for composition, you know, when we're doing the derivative of composition, there was an inside function of the parentheses. If I see something in parentheses right here, that is my number one candidate for the U substitution. So I usually take that and say, okay, so U is equal to 3x to the third minus 50. And then we find the derivative of that. So what is du going to equal? Well, this is going to be a 9x squared. Okay. And then dx. Okay, so usually for constants, I do recommend highly that you then take this and divide by the 9 or multiply by 1/9. Do it as a 1/9 because you're going to do something with it later. And this gives me x squared dx. When I look over here, I need to see all of that, which I do. There's the x squared, there's the dx. This is a constant, so we're going to move out to the front. And then I can start replacing things. But you have to have that derivative in there, the variable portion of this derivative in here, for you to use U substitution. So once I have that, this 2 is going to come out in front. This right here is, all of that becomes U to the 20. And then this piece becomes 1/9 du. And then the 1/9 will come out here with the 2. And now what I have is I have a simple power rule for integration that we can do fairly easily. We weren't able to do it up here, but now we can in this form. So this here becomes 2/9, and then we raise the power 1, divide by the raised exponent, plus a constant. But I need to put back what U stood for, so I'm going to now take this right here, and I'm going to just put it back in, and this is going to be times, and this over here will be 3x to the third minus 50 to the 21st power divided by 21, and plus a constant. And so we can clean this up more, bringing the numbers together and stuff like that, but that's basically our answer right there. So the next one we have is this one right here. So again, we look at it, and we see stuff in the parentheses, and so our first instinct is to say, okay, we're going to try U substitution. Anytime you see something in parentheses, your first instinct should be to try to do U substitution. It's your number one go-to. So then I set this here equal to this, and then I take the derivative of it with respect to x, and I get that right here, dx. The constant we don't care about, because that's just going to come over here as 1/2. And this is going to be x dx. What I need to make sure of is that this is there. Is that over here? And there's the dx, but there is no single x anywhere for that. So this tells me that I cannot use substitution. This does not work for this, so we have to find an alternate method. And that method was simply to multiply this out. Multiply it out. Okay, so this quantity times itself will give me x to the 4th, 10x squared, plus 25 dx, and then I can just integrate this using our normal techniques. Raise the power 1, divide by the raised exponent, oops, not an equal sign, but a minus sign, 10, raise the power 1, divide by the raised exponent, and then 25x plus a constant. Okay? So, if you can't use substitution, then you can't. But you have to go through this process, and that's what you normally look for first. You don't want to just jump in here and start multiplying things out, although you can if I can use substitution. Okay? So let me go ahead and show you some of the notes I wrote for this one so you can see it. So we have that one already. So here's this again, the one I just did. I'm going to pull it down here and give you a moment here to write that one down. So go ahead and pause and write that out. Okay, and here's the bottom one down here that I just did. So pause there and write that one out. Okay, let's go look at another example. So in this example right here, we have the tangent of 3x. So when we look at this right here, we want to first look, as always, we want to look, do I have this rule? But I also see that I have something in parentheses. And so do I use substitution, or do I have a rule? In this particular case, we actually have a rule for this. Okay, and so you can then use the rule to assist you. But I'm going to show you how you can do a trig function if you didn't know the rule. So normally what we would do is, we would usually use substitution be the stuff in the parentheses, which would be the 3x. But in this case, again, I don't have a rule, let's say, or whatever I need to do, but I can do trig identities to change what this looks like. So this right here, tangent is sine over cosine, the quotient identity. I can write this as the sine of 3x over the cosine of 3x. And when I do this, now I have two trig functions in this problem. And if you have more than one of them is usually going to be your u. When you have a fraction, your u, your first instinct for the u is going to be the one on the bottom. Okay? So and that's what happens in this case. We're going to let u equal the cosine of 3x, and so then its derivative, the cosine is minus the sine of 3x, don't forget, times 3 dx. Got to do the chain rule. So this 3 and this negative are going to come to the other side as a negative 1/3, and I have the sine of 3x dx. Do I have that in my problem? And the answer is yes, I do. There it is, the sine of 3x and the dx right there. So I can use substitution. And then this problem then will become the integration 1 over the cosine, so 1 over u. And this over here is going to be a negative 1/3 du. The negative 1/3 comes out in the front, and you end up with 1 over u du, and we have a rule for that, that is the natural log. So this becomes a negative 1/3 times the natural log of u plus a constant. And so putting back what we said u was, this is now the cosine of 3x plus a constant, and there is our answer right there. I don't know if you can see, I got something blocking it, so I'm going to move it here just a bit so you can see it. So there's the answer there. Okay? So let me go ahead and show you what the side notes I had for that one, so you can take a look at it. So take a moment right here, pause, and then you can copy it down. Okay, let's go ahead and look at some more examples now. So now I have an E. So in this particular case right here, what I'm going to do is I'm going to choose a U in this scenario. Which one do I pick? Well, you want to pick something that you can take the derivative of and have that left over. So the first thing you want to do is, if you have anything, an x and an exponent, choose the exponent. So choose the exponent as your U. So the derivative of this is going to be, remember this is x to the 1/2, so this is going to be a 1/2 x lower the power by 1, okay, dx. So the 1/2 here, I'm going to move over here as a 2, so now I have 2 du equals, and then I'm going to change this to the positive, so it'd be 1 over the square root of x dx. And do I have that? Well, there's the 1 over, and there's the dx, so yes, I have that. So this is a candidate for u substitution. So this becomes e to the u, and then times 2 du. So then I just simply pull the 2 out in front, and then I can just integrate this quantity, e to the u plus a constant, and then put the u back. And there's my final answer. Okay, so always try the exponent first if you have it, like in this example right here. Same thing again. Okay, notice the difference here though is I have limits. So how do I do limits? Okay, well just remember we have the fundamental theorem of calculus, so it tells us how to do limits. So we're going to evaluate with these things once we get done. Other than that, the process is exactly the same. So we want to pick a u. So we always want to start with the exponent to see if that one works. If it doesn't, we will pick a different u. So this is going to be 8x dx. So then this gives me 1 over 8 du is x dx. And do I have that? I have an x and I have a dx. I am good to go. This 3 is going to move out to the front. So now I have a 3. Oh, one more thing though, with limits. I'm going to start, before I start substituting stuff in, I need to remember that these are limits for x, and they also need to be substituted. So how do I deal with the limits? What do I do there? Well, I have this little connection right here. I said let u equal that. So for our limits, when x equals 0, my u is going to be 4 times 0 squared minus 1, or negative 1. And when x equals 5, up here, then my u is going to be 4 times 5 squared minus 1, or 99. So we're going to substitute everything in here now. This is going to be, the 3 comes out like I said, the 0 becomes a negative 1, the 5 becomes 99, the e to this will be e to the u, and then x dx becomes 1 over 8 du. And then we're going to move that the 1/8 out in front. So now I have 3/8. You want to do all this to make sure you do it properly. Okay. And so now we're going to integrate. Now because I have limits, I'm not putting a plus c. I'm going to put an evaluate. So this right here becomes 3/8 e to the u evaluated from negative 1 to 99. And if you remember how we do this, it's going to be the upper limit minus the lower limit. The 3/8 is just a constant times, so I'm going to put it like that. This will be e to the 99 minus e to the negative 1. And there you go. That's how you do your limits. Okay? So I'm going to pause right here before we do the next example here. I want to come back over here and let you write down some more notes that I had on the side. So right before I did that problem right there, limits using the fundamental theorem of calculus allows me to write it in this fashion. That's what we use down here. Okay, and then I have this little things on how to pick what you're doing. So take a brief pause right here and copy that down. Okay, let's do another. So now I have this one. All right. So usually when you have a rational function or a fraction like this, you usually want to choose the bottom to be your u. Not always, but that's where you want to start. So if that's 3x plus 1, then my du is going to be 3 dx. And I'm going to move this over to a 1/3 du is dx. I have a dx, we're good to go. This 2 is a constant that will come out in front. I have limits, so I need to change those also. So for my limits, when x equals 1, then u equals 3 times 1 plus 1, which is 4. And when x equals 5, my u is 3 times 5 plus 1, or 16. So let's go and start plugging things in and substituting stuff over here. Here's that 2. The 1 becomes a 4. The 5 becomes a 16. This is going to be 1 over u times 1/3 du. And then move this out to the front. It gives me a 2/3. 4 to 16, 1 over u du. And we see that we have the natural log. So this is going to be 2/3 times the natural log of u. Evaluate from 4 to 16. So you simply plug it all in. It is the upper minus the lower, and there you go. If simplification could be allowed, could be achieved, then you would do so. Okay? All right, let's take a look at some more examples. All right, so here we go. It's another one. So again, we have trig functions. We look at this closely. I see 2 trig functions in here. I look to see if it's a rule. Do I have a rule for this? And I don't. But what I do want to look at is this. If you have more than one, the first thing I want to do is one of them the derivative of the other? If I chose that for u, its derivative would be secant squared. See, I have it. So that's how I choose my u. If it wasn't, I would try that one. Is the derivative of this the tangent? And the answer would have been no. And so then I wouldn't have done that one at all. So the derivative of the tangent is the secant squared of x dx. And you can see then that I have it. So then this problem here, and we have limits, so we have to do our limits. So when x equals 0, the tangent of 0 equals 0. And when x equals pi over 4, the tangent of pi over 4 equals 1. So let's do all of our substitution over here. So this is going to be the integration from 0 to 1 of a u du. And so then let's use our rule. So we raise the power 1, divide by the raised exponent, evaluate from 0 to 1. And so then I plug in the upper minus the lower, and I get 1/2. So as you do these things, don't panic, don't get confused by what you're looking at. See things in the bigger picture. If I have something in a parenthesis to a power, then that's most likely what my u is going to be, no matter what it is. And so try it and see if you have the derivative. If u is the natural log of x minus 1, what is du going to be? Well, the derivative of the natural log is u prime over u. So 1 over x minus 1, then times the derivative of that stuff, which is just 1 dx. And there it is. It's on the bottom, and the dx. So now we do our limits. So when x equals 2, u is going to be the natural log of 2 minus 1, which is 1. And the natural log of 1 is 0. And when x equals 4, u is going to be the natural log of 4 minus 1, which is 3, which is just what it is. And so we plug everything in, just like we've been doing. 0 to the natural log of 3, and u becomes u squared, and then du. And then we're going to raise the power 1, divide by the raised exponent, and evaluate from 0 to the natural log of 3. So I have the natural log of 3 cubed over 3 minus 0 cubed over 3. So it's just going to be 1/3 the natural log of 3 cubed. Okay? Now let's look at that one. This is a radical. This is the radicand. So most of the time, that is what you're going to choose for your u. So u is going to be x plus 1. So then du is going to be just simply dx. Okay? And so what happens here is I notice, oh, okay, I have that, but what about that? I don't have something for that. I can replace that. I can replace that, but how do I replace that? And so that brings us to this unique situation, an extra variable. How do I deal with it? You can deal with it right here. If u is equal to x plus 1, then I can rewrite this as x equals u minus 1. And then I can replace things according to that. So that means this becomes the integration of u minus 1, and then this right here becomes the square root, which I'm going to write as a power. So this becomes u to the 1/2, and that becomes du. See how I replaced every quantity in here with a value of u? And then I can then do this, distribute, and rewrite this in power form. U to the 3/2 minus u to the 1/2 du, and then I can integrate this quantity right here. So raise the power 1 divided by the raised exponent, raise the power 1 divided by the raised exponent, plus a constant. So I'm going to flip these over and change and put back the u. So this final answer here then is going to be 2/5 x plus 1 to the 5/2 minus 2/3 x plus 1 to the 3/2 plus a constant, and there you go. So what about the next one? This one right here is another kind of a unique situation because you can do it two different ways. All right, so whichever way works best for you, or which way you like better, or whichever way you recognize. Okay. If I do it, I'm going to show you both ways. Okay, both methods side by side. Okay, we're going to do both methods side by side. And the first method over here I'm going to use, and I got to write kind of small because I might need more room. So our first method right here is u substitution. So let's let u equal the bottom. And so du is going to equal to 2 dx, which you know we're going to change to 1/2 du, like so. Okay? When I do this, you can see that I don't have that x that's up here. If I look at this top part, I can factor the 4 out, and I'm going to have an x plus 1 on top, and I don't have that. So I'm going to do what I did with this one, the one above. I'm going to solve this one for x. So x is going to equal u plus 1 divided by 2. And I'm going to start replacing this problem with that. First off, factoring the 4 out to the front. So it's going to be 4. And then on the bottom of this, we're going to have a u. Okay. The dx is going to become 1/2 du. And on top, so visualize it, x plus 1. So the x I'm going to write as u plus 1 over 2, and then plus a 1. So our task now is to clean all this up, to simplify this out to a point where I can then do integration rules with it. So on top, I can get a common denominator of this right here is a 2, so this would be 2 over 2. Combined with this over here is going to give me a u plus 3 over 2. So separating things out so you can see it, there's the 1 over u. And this is going to be x plus, excuse me, not x, u plus 3 over 2, and this is still 1/2 du. So that 2 and that 2 can come out to the front here with this and cancel with that 4. Okay, and so then I'm going to have this times that gives me a 1, so just kind of walk with this out. So 1 over u times u is 1. 1 over u times 3 is 3 over u du. Okay, so I'm going to write just a little bit smaller. I need like 3 lines here, and I only got room for 2. So this right here is going to become u. This is going to become 3 times the natural log of u plus a constant. We're going to put back the u, so this is going to be 2x minus 1, 3, the natural log of 2x minus 1, plus a constant. Now I want to show you something. You see this constant right here, this minus 1, and this constant over here? You can combine those two together to bring a brand new constant, and you get this answer right here like this. So if you want to see where a constant disappeared in a problem where you have c, that's what happened. All the constants get merged into a new constant, so this is not the same constant as that one was. Just like this is not the same constant as that one is. We just keep calling them constants. They keep changing, but we don't really care. So then we have this answer right here. So this is a u substitution approach. The other method we can use, method number 2, and we're going to explore this in just a minute. This is a new technique, and that's called long division. Okay? Because these are both polynomials and I'm dividing, I can do long division to simplify this out. So we would take the top divided by the bottom and do our long division techniques that we learned in the previous years, and this is going to be 4x minus 2, change the signs, and I get a 6. That means this expression right here can be changed to be this, 2 plus the remainder over the divisor, dx. Now, as I do this, you can see that I'm going to split this integration. I only need to do u substitution when I need to use it. I don't have to keep doing it all the time. So that means when I split this apart, I'm going to get the integration 2, this is a constant, comes to the front, 2 dx, plus, then I'm going to have a 6, 1 over 2x minus 1 dx. Only this one right here do I need to do a u substitution for. And that would be 2x minus 1, so du is going to be 2 dx, and so then I have the 1/2 du is the dx. So this one I already know the answer is going to be this, so this is kind of like a mid form. You can do this off to the side. I don't want you to get a problem wrong if you merge these together, but this will be 2x plus a constant that I'm going to save for later, and then this over here is going to be 6 1 over u 1/2 du, which is going to come out as a 3. So don't put u's and x's together. This is really kind of bad form here, but it makes it easier to do. This will be 3 times the natural log of u plus a constant, and then replace that back. 2x, 3, 2x minus 1 plus a constant, and you can see then I have the exact same answer both ways. Okay, so I'm going to move this over here for a second and give you a chance to come over here and write down some of these side notes that I had, starting with that one. So go ahead and pause the video, and you can write some of that stuff down. And I'm going to go into some more examples. And so here's some more down here. Okay, let's go ahead and look at some more examples that I have. Here's another long division problem that I have marked over here. In fact, the next two are showing illustrating the long division techniques. So I'm just going to go through them fairly quickly for the sake of time. Actually, I'll just show them to you because the video is getting kind of long. So let me just go ahead and show you how they come out, and then you can pause and write them out as you see it. So the first thing I did, especially here because the top polynomial is much bigger than the bottom one, I did long division. Okay, replace that fraction with the long division that I have, integrating each individual piece. Only this one am I doing the U substitution for. Okay, these other ones I can do fairly easily. So once I have this one and I clean it up, the 1/3 comes out with the 5, and I'm going to have the natural log. So instead of doing an extra step in here, I just replace the U with it right off the get-go, and I have this final answer right down here. Don't forget to change back. You don't want a final answer that has both U's and X's in it, so make sure you do that, okay? This next one has a neat little thing in it that you want to be aware of. Again, polynomials, long division, and then when I have this right here. So when I have this part right here, what do? Okay, I can do a long complex U substitution, which would work, but I can also do this. I can split this. Remember, this is just fractions. So I can take the top divided by the bottom and this top divided by the bottom and split it apart. Be very careful of your signs as you do this, okay, so that you have the right sign for the right job. And so now I have 4 things here that I can integrate each individual piece. This one I can integrate no problem. This one I can integrate no problem. This one is a U substitution, right? And I get that, I'm good there. But U substitution doesn't work for this one. If I take the derivative of that, I'm going to have an extra x that doesn't have it. So what I have to do is I have to look for another rule. And then luckily for us, we have another rule. This is actually the inverse tangent property. So then doing all of these problems individually and then replacing the u's back gives us our final answer down here at the bottom. So just be very careful and take your time as you go through these examples. Make a note of different things that you are doing, okay? And so on. Here's another one down here I want to show you. This one is already in the proper form. And you will note, especially when you see a fraction with a square root in the bottom and things are squared and stuff like that, you should be thinking inverse trig functions first. You can try U substitution, but when I take the derivative of this quantity down at the bottom, I'm going to have an extra x that's not available, so I have to try something different. So this one right here is I'm just showing you how to go about and do and match the rule so that you get the right quantities that you need. Even though this has a 5 sitting right here, I can treat that as U squared. See what I did? That is A squared, so A is 1. That whole quantity is U squared, so when I square root it, I get that quantity. That's my U. Take the derivative, and I have that. So I just have a constant, and that's good. We can do that. Then I can do the U substitution technique, replacing everything out. And then this is my replacement for dx. That square root of 1 over square root of 5 comes out to the front, and this is the inverse trig function, and then replace the u back. I like the radicals last. It makes it easier, so I don't have a, so it doesn't look like the x is underneath the radical if I get sloppy. So be aware of that, okay, as you look for those things, how to go about doing that problem right there. All right, so we have some more. A new technique, the last technique, okay? Doesn't happen very often, but it does happen. back when I told you guys about completing the square, I said there's a couple instances where it occurs, and this is one of them. So here's a quick rehash of completing the square technique. If I have x squared plus some bx plus some constant, don't really care about, then I want to write this in the squared form, then I'm going to complete it. You take the middle number with sign, you cut it in half and square it, and if I add that to these x terms here, I'm going to get a perfect squared trinomial, which I can then write as a squared like so. Whatever I add, I must also subtract the same quantity, and so this over here will become a new constant. So this is the complete the square technique. I'm going to walk you through an example on how to go about doing it. Again, I'm just going to show you the answer so that you can see how it's done. And I chose a really interesting one here so you can see it all the way. That it doesn't matter how ugly it looks, you can still do the problem. I'm going to talk about some things as we move along. So first off, there is clearly no rule that we have for this. I cannot do U substitution for this. So my first thing that I'm going to try then is completing the square to see if I can get into some trig form, inverse trig form. To do completing the square, the x squared term has to be positive, a positive 1 coefficient, so I'm factoring out the negative 5. So if you look at what I did in here, all I did is I left the 1 where it was and I factored out the negative 5 from those two terms, and then this is what I end up with right in here. So I'm going to complete the square with those two terms right there. So I take the 10, positive 10, cut it in half as 5 and square it. There it is. So I'm going to add this quantity right here inside. But remember, if I distribute this negative 5 to that, that's going to be a negative 5 times this quantity. So since that's a negative 5 times that, I need to add the exact same thing. I have to offset it. Okay? And so this is why you see that number over here. So this quantity here becomes this, and that's 125 plus 1 is 126. So now I have this form right here. I'm hoping to get it to be an inverse trig function. I have something minus something that could be squared. So if I say that's a squared, then a is that. U squared is that quantity right there, so u is that. Take its derivative, move things around, and then I can do u substitution. And so that's what I did over here. And then recognizing this as the inverse sine function again. Plugging things in using the rule. Okay? And so I have that right there, which gives me my final answer over here. Make sure you put back your x's. Okay? So that's the technique right there. I have another example. Actually, I have two examples. And so I'll just go ahead and show it to you. So here's the next one. This one, there was no radical in the bottom, but I had a polynomial. Okay? I want to try and do something with this. I mean, I don't know what to do. I can't do a u substitution or anything like that. I've tried all the other options available to me. I tried factoring this because maybe this will be something, a quantity that's perfectly squared. So you want to make sure you try and factor things if it's possible. Because if I had like a x plus 3 squared on the bottom down here, then I can do the power rule technique. So always try and factor things. But I can't do any of that stuff, so I'm going to try completing the square. I'm taking the completing the square with the x stuff. So if I look over here, you'll see that I took half of the negative 4 and squared it. That gives me positive 4, so I have to subtract the exact same thing again. So these first three terms here will become the perfect square, and these things will combine to a new constant, and that's what you see right there. So I have something squared plus something squared. A squared is 5, u squared is this, so a is the square root, u is this, and now it's my du, and I can use u substitution. And then this form right here is the inverse tangent. Okay, and so then I just plug all of my numbers in, and there's my final answer. And then the last one down here, pretty much the same thing. I was just walking you through again. It's the same rule again, but this time there's a number in front of the x squared again. because you have to first start by factoring that out. Okay, you take out the 2 of the first things, like that. Okay, then you can figure out what the number is you're going to square. So half of -2 is -1. So that's going to be 1. And 2 times that is 2. So I need to subtract 2. Combine things together. This whole quantity is my u squared. That's where the square root of 2 is coming from. Okay. Plug things in. Integrate it. Plug your numbers back in. Final answer. So a lot of things you got to practice on. 3 different techniques in this video. But u substitution is your number one go-to. You're going to do it almost 95% of the time, if not more. Okay? So all things through, just like in derivatives, all things were through the chain rule process. All integrations, you start off with u substitution if it's not already in the proper basic form. So that ends our video here, and we'll do more problems together.